for joining the talk today. Of course, my name is CJ Reddy. As Eric mentioned, I am the VP of Business Development for Electromagnetics in Americas. So today, we'll focus. Of course, we have a series of webinars, and today our focus will be on installed antenna performance and mitigating the core-site interference or computing the core-site interference when there are multiple antennas are there. And probably some of you know us from Feko side, but some of you maybe from other disciplines. But lately, Altair has been expanding the role of simulations in electronics and broadly, I guess. So we have electronics design that includes the PCB analysis and so on and so forth, but also through Feko, the antenna design and the placement analysis, and of course, going beyond the propagation and connectivity and those kind of things, which we'll cover in the subsequent webinars. On the mechanical side, we can do structure analysis, stress, vibration, drop test, and those kind of things, thermal as well, with a cooling, both forced cooling, natural cooling, mechatronics, and circuit analysis as well through our Activate tool via SPICE coding. And also, of course, we can generate embedded coding for controllers and those kind of things. And also, all of them support high-performance computing as well as scheduling and cloud accessibility of the simulation tools that we have. So focusing mostly on the electromagnetics here, we have tools for antenna design. That's one of the things we're going to cover today, and also antenna placement and coupling, but also virtual drive tests, flight tests for platform and connectivity, even if you're in automotive, I guess, the ADAS simulations, and electromagnetic compatibility through the cable modeling, radiations, shielding, so on and so forth, radio and radar coverage and planning, focus of one of our webinars in this series, including the scattering and RCS. That's also another webinar we're going to do on the scattering and RCS. Of course, the capability includes a radiation hazard, bioelectromagnetics, RF devices like waveguide circuits, and radomes, and including FSS. This also will be covered in the radome webinar we'll have in this series, because radio frequency interference as well as spectrum management. So you can see that we can not only do a very detailed antenna design placement, but also broader system design using the tools that we have. Of course, the focus today is on antenna placement, which is actually a very, very critical thing in antenna design in a communication system. Where you place the antenna could change your antenna radiation pattern. That means your system design should take into account the pattern as it is placed, but also you should find a place where it can be well performing for your communication requirements. One of the things that Feko has been able to do this right from beginning. We're actually a standard, industry standard in antenna placement, is because of the multiple solutions we have in our tool chest in the Feko software suite that includes not only FEM, finite element method for highly inhomogeneous objects, finite difference time domain, method of moments, MLFMM. All of them are the what we call the full wave solutions, but also the asymptotic solutions like physical optics, Lagrangian geometrical optics, uniform theory of diffraction that can be very useful for as you go to the larger electrical sizes in analyzing the radiation patterns. But of course, they're also hybridized, as you can see with these arrows. The FEM is hybridized with method of moments, and also MLFMM, method of moments with the physical optics and RLGO, as well as UTD. But we also have an iterative method where MLFM is also hybridized with the physical optics. So you can use physical optics on one part of your problem and MLFM for the other part of the problem. We use what's called an iterative method to converge the coupling between the both parts. And this is actually one of our key strengths in the industry, not only for designing of antennas, but also for going further, I guess, in terms of antenna placement analysis. Of course, all our solutions or solvers are parallelized on multi-core CPUs and multi-CPUs, of course, with the shared memory, large-scale clusters with the distributed memory. And of course, we also support out-of-core solution if needed. You can see that the scaling that was done for one of our solvers goes all the way to 960 cores with a speed of 10 times compared to 60 cores here, scaling very linearly over the CPUs and cores. So one thing that is normally needed for many of our customers is that when the platform models come to them as an antenna engineers or electromagnetic engineers, they come from mechanical models. So, mechanical people doing the stress analysis and those kind of things. Those models come to us for antenna placement. So if it is not too complicated, we have tools in CAD Feko to fix them. Some small things like CAD fixing tools. But of course, it is too complex for CAD Feko. We have a tool in Altair portfolio called HyperMesh that can do CAD healing and mesh healing and can deal with very complicated structures and defeaturing and making them suitable for Feko analysis. We recently introduced in HyperWorks a profile called Feko profile that in a way understands what Feko needs and and also translate the mesh in a way Feko can read, including the material properties and all those things. So that's an additional benefit we have in Altair. Of course, with our licensing system, you're not buying these tools separately. You have access to all these tools at your disposal when you have an Altair license. So we can do, this is actually the first step, but anybody goes through when they have a very complicated geometry tool for antenna placement. And some few examples of how our customers have been successfully using Feko for their platform install performance. So for example, this is from Airbus helicopters. One of the users, their expert users, he gave a video testimonial on how they are using Feko to optimize not only placement of antennas for the communication system, but also use of the composite materials. Feko allows for use of composite materials for your platform structures. So how do you place your antenna and also make sure that the antenna works correctly on a composite structure can be analyzed using Feko, and has been successfully done by Airbus helicopters. Here in the US and Northrop Grumman, of course, one of our longtime users, Scott Burnside, he has successfully used not only Feko, but also our other tool called HyperStudy. This is actually that can be used for what I can call as a machine learning approach for design and optimization. And Scott has been able to do this very effectively for his work. And of course, he has given us a video testimonial at this link that you can access. We can share these links with you and also the slides with you if you need it, so you can take a look at these video testimonials. And also there's a paper published in 2012 by Saab actually on computing the radiation patterns using Feko on a Feko model, but also doing the scale model measurements and then comparing those things with the measurements, simulations with the measurements. You can see that the blue line here is the simulation and the black line is the measurement. You can see quite nicely how it is tracking in different planes. This is azimuth plane and vertical cut and a vertical cut in another plane here. All of them are validated well by Saab, I guess, with their scale model measurements. Another example is by CNES. This is part of European Space Agency, where, of course, again here in a scale model of a rocket launcher, and there they took a monopole and put a, this is, of course, they're doing just for the sake of validating simulations with the measurements. So when they have their real antennas and real obstructions, they can rely upon the simulations. As you can see that both simulations, that is the blue line, and measurements, this is a red line, agree quite well in both planes, that is P equal to 0, P equal to 90. Of course, a little bit earlier, I guess in 2005, there was a paper at APS Symposium on placement of an antenna on a large aircraft, both for, of course, this is done for VHF 126 megahertz, where you can apply both metron moments and MLFMM and compare with the measurements. Of course, in the 1 gigahertz range, here they applied physical optics and compared with the measurements. You can see that quite nicely how the simulation data tracks with the measured data in this case. So there's a lot of confidence in Feko in antenna install performance in the industry for, of course, as an industry leader, I guess, in this one for many, many years. One of the key things in such simulations, install performance, is a method called multi-level fast multipole method, which does not make any physical approximations, but has been very effective for electrically large structures in terms of reducing the memory and reducing the computing time. You can see that we could simulate not only an antenna array, this is around 100 plus antenna elements, microstrip patches, not only the array itself, but also array on the satellite could be analyzed with MLFMM that took only 6.6 gigabytes versus could taken close to 1 terabyte with the micro moments. I'm sure 1 terabyte we did not do the simulation, but if we were to do the simulation, time that is taken for that would be much, much higher compared to what MLFMM would take for those simulations. Of course, another example of the recent improvements we have in MLFMM is that in 2019 version, let's say for this problem, if you go back, I guess, is that Hammer at 2 gigahertz. And for this particular problem, it would have taken 188 gigabytes with 1.7 hours of the runtime. You can see that in 2021, we could reduce that, I would say, I think 30% to what is 188 is close to 200 to 43 hours with 0.83 hours of the runtime with the 20 parallel. So we have been constantly improving MLFMM for its speed and also memory performance. So changing a little bit the gears here, typically when you have to do the installed antenna performance, you own the platform or you have the platform. Most of the time, the vendors supply you the antennas. Those vendors may or may not give you the full simulation model of their antenna because of the intellectual property limitations and for many other reasons, I guess. So Feko allows you to do what's called model decomposition. That means you don't have to have a physical antenna CAD model or a physical antenna simulation model for simulating installed antenna performance. You can have the near fields from the antenna or far fields from the antenna, or you can have spherical mode sources and use these ones not only as the radiating sources, but also receiving antennas. This way you can do the coupling calculations and so on and so forth with those equivalent sources. So here is an example of various antennas that are there with a transmitting antenna here, and the coupling is computed by received power divided by transmitted power with the 10 log, of course, with the dB between various antennas and can be plotted. So this is already in the Feko calculation engine where you can use these equivalent sources to compute the coupling. Of course, because they're equivalent sources, we don't take the mismatch into account, but now, nonetheless, you can do the coupling calculations or isolation calculations using these methods. Other thing one could also do, I guess, is we actually teamed up with a measurement company called MVG, Microvision Group. They have a spherical near field measurement system. And from their spherical near field measurement system, they could create a very compact near field source that can be used in Feko. So what we have done working with them, they took a bicone antenna that is on a plate like this one, and they have done measurements of this bicone antenna, its radiation pattern, but also they could measure the near fields of this bicone, very close to the bicone in a box like this one. So we obviously, because this is, we're collaborating with them, we have the simulation model of the bicone. So we could simulate that using Feko, this model here, that is the red line. And the blue line is using the measured near fields that MVG has provided us, and that on the same plate. That's the blue line. And of course, the actual measurements done by MVG of this plate with the bicone, that's the black line. You can see very good agreement between the equivalent source as well as the simulation model and measurements here. So we thought, we'll extend this to a little bit more complex a platform like a helicopter here, placing this on the top of this rotor blades here, the antenna here. Because we have the simulation model, we could place that on the top of the helicopter, but also the equivalent sources. And you can see that both of them agree quite well. That means if you were to use a simulation model, that would be the red line, and the equivalent source is the blue line. And you can see that even nicely tracking all these ripples. So very, very accurate, I guess, in terms of radiation pattern calculations using equivalent source. Of course, there is another technique that we have in Feko called characteristic mode analysis, CMA, that can be used for placement of antennas or designing the platform mounted high frequency antennas where 2 to 30 gigahertz or so, 30 megahertz or so, where platform itself can become part of the radiating structure because of the wavelength size of the platform. So this is actually a case study done by Ting-Yan Shin and Nader Bahadar at University of Wisconsin-Madison, where they won the Feko Student Prize Award for this one. There is a webinar available for this where you can watch the complete webinar. Essentially, they took the vehicle, they computed the characteristic modes of the vehicle so they can decide where to place the antenna so that the complete structure, not only the antenna by itself, but also the whole vehicle here can radiate what is needed for this application, that is the NVIS application, where it has to look up in the sky for the reflection from the ionosphere and so on and so forth. So that's also available in Feko for this kind of calculations. So one of the things that most of the antenna manufacturers have to do, I guess, is not only meet the electrical specifications, so that frequency, bandwidth, gain, and input return loss, and those kind of things, but also they have to meet the MIL standard 810 for the shock, temperature, vibration analysis through a mechanical design. And with Altair, we have multiphysics analysis, not only electromagnetics with Feko, but also we have a product called OptiStruct, where you can do thermal analysis, you can do vibrations, you can do shock, and so on and so forth. So we actually took a blade antenna and mounted on an aircraft kind of a structure. You can see that we use these 4 bolts to attach this to the frame and could compute the displacement or vibrations because of the MIL standard 810 specifications. So, of course, I'm just giving you a brief preview here, but we have a complete white paper on this. If you are interested, I guess we can share that with you. As I mentioned earlier, because of our licensing system, the way it works, if you have access to Feko, you already have access to these tools as well to do further analysis. May not be you as an antenna engineer, but your mechanical counterparts at L3 Harris. So coming to core-site interference, of course, this has been there in Feko for a long time. When you have multiple antennas on an aircraft like this one, like UHF, COM antenna, GPS, and so on and so forth, you can compute the S parameters, the test matrix for these antennas here. But we also have a script where it can show you can set the limits and say less than 60 dB coupling is good, that's our green. And if it is, of course, between 50 and 60, that could be, something to look at, yellow. And of course, if it's less than -50, then you have to be careful about that coupling between those two. So we can plot a matrix kind of thing based on the limits you have set. That's what we had this for a long time, but recently, that's a year or two ago, we added a technology called RAP. RAP actually is a propagation tool that can also do the co-location interference analysis, and we extended that to platform core-site interference analysis. So here, RAP can take into account intermodulation products, IF breakthrough, image frequency, harmonics, transmitter spectrum, receiver selectivity, and receiver blocking. All of them into account, but also take the communication protocol spectrum is also supported for this kind of calculations. So as an example, you have a GPS antenna on the top and COM antennas on the bottom. We can actually compute the adjacent channel or a co-channel interference, it can give you. So basically what you do is that in Feko, you compute the S parameters of these three antennas and bring them to RAP as what we call a coupling loss matrix. They call in RAP terminology, S parameters are translated to coupling loss, and that can be input. And from there, we can actually, RAP has some equipment specifications already filled in, but you can also put in your own equipment. If you have a GPS receiver, you have a COM transmitter and receiver, you can put in those values, and we can compute the co-channel interference with a margin. Of course, the lower the margin, not good. More number we have with a negative will be better. So we can compute between various receiver here and the transmitters and so on and so forth. So that takes you one step further to what is actually needed. Though I have not presented here, maybe we can look at it later on when Raja demonstrates, is the filtering of the trans receivers. So that's also possible in RAP. You can put a filter and then see in simulations and see how well this interference can be mitigated and the margin can be improved. So as I mentioned, we can also do interfering signal level analysis. Typically, this is done for propagation, where you have an area where multiple transmitters and receivers are there. But you can also replace the propagation calculation with the results from measurements or Feko and other tools as well into this to compute the interference signal levels, and also beyond that intermodulation products, harmonic levels, and those kind of things. With that, that's kind of my presentation. I want to leave enough time for Raja for demonstration of the co-site interference analysis, and he will be doing a ship-based co-site interference analysis, not only from Feko side, but also more importantly on the RAP side. How do you do this further analysis with the trans receivers and those kind of things? With that, I hand over this to Raja for the demo. Let me unshare my screen. Raja, you should be able to share your screen.
Sure, Dr. CJ. Sure. Hope you could be able to see my screen. Please let me know.
Yes.
Yeah.
Yes.
Thank you, Dr. CJ. Thanks for the nice presentation, Dr. CJ, and it's really good with all the antenna placement studies with respect to the simulations and measurements. And now I would like to present a short demonstration on the antenna placement and co-site interference analysis. In this particular demonstration, I will be using the CAD Feko and post Feko tools, as well as the tools. Those are the modules that are available in Feko. And also I'll be using a RAP software to calculate the co-site interference from the S matrix, which we obtain from Feko. Let me start setting up the model in Feko over here. Yeah, I'm going to launch the CAD Feko. Yeah, I have my CAD Feko is launched over here. I would like to import the model. I assume that I got it from my vendor or some mechanical department. I would like to import a ship model over here into my CAD Feko session. I think you can import you can import the geometry, you can import the mesh, and several formats are supported using in this particular thing. You can see over here in importing the geometry, you see a lot of file formats that are supported. It's Parasolid, Model IGS, ODB++, and lot of file formats are supported. I would like to bring a Parasolid ship model onto my CAD Feko session. Okay, I'm going to have my ship model available, and let me import this particular thing into this particular thing. Of course, if you have any issues with your meshing, you can go back to, as Dr. CJ mentioned, you can go back to take this model into hypermesh, and you can clean the geometry, and you can bring this back to here. If it is very simple mesh issues, definitely you can treat those issues inside Feko itself. And as usual, this is very important. Like we do go in the workflow like all the time from left to right. Okay, in setting up the model, we just use the construct and transform traps for creating the geometry. Of course, here in this particular case, we imported the geometry. Of course, source or load tab, we use this particular thing for the excitations and frequency setup. And the request for the output parameters, it might be far fields, near fields, currents, etc. We are going to do that particular thing using request tab. Then of course mesh, we'll be meshing that particular thing, which we just spoke about that particular part. Then we'll be going to the solver run for any solver settings, and then we can use the Feko solver button that is available in Feko solver. Okay, I just import, as I told, just I imported my geometry into CAD Feko, and let me assign few things to this particular thing. I would like to define the media over here. I would like to go to the construct tab, and I would like to define a media, so that I would like to use this particular media properties to the ship and the seawater, that which I would like to assign appropriately. First thing is my seawater. I would like to use a seawater uh, uh, dielectric medium. I know the dielectric permittivity of this particular seawater is 80, and also the conductivity of this particular seawater is 4. I will show you appropriately. I would like to tag this particular thing to the surface. Okay, then I just wanted to change the display color so that it will be blue, because the sea will be in blue color. I would like to use the dark blue over here. Then the next thing is I would like to bring the other media property is steel, that is available over here. Of course, I'm going to define it again, and I have the steel metal property, so that 100 is the relative permeability of this particular steel material. And of course, I do have the conductivity 1 is 6. I do have the steel, and again, I would like to change this particular color so that it will be elegant. I just need to use little bit, just it will give the much more brighter for visualization purposes. Okay, I have my steel material is available. I would like to assign the faces of this particular ship to the steel material. Okay, let me choose all the faces of the ship in this particular thing, and let me assign to the steel material, of course, which is having a finite thickness. I am going to apply this particular thing so that it is, I have a ship with the steel surfaces. Then I would like to have the sea surface. That means, assuming, because usually the ships are going to go on the sea surfaces, we have the two options that are available in Feko. You can do either a rough sea surface or a smooth surface based on your choice. We do have other options. Both the options are available. Here in this particular case, I will be using a smooth plane surface of the water. I will go to the plane or ground. Then I would like to assign homogeneous half space in G less than 0. And of course, it's automatically tagged with the seawater. Okay, you can see over here the medium is seawater. That means we got a ship and we got a sea surface. Okay, it is available. Then in case if you would like to use the rough sea surface script, definitely it is available in the home tab under Mac application macro library and model construction. You can see over here, create rough sea surface. One can use this particular script to create the rough sea surface. I'm not doing that. Just I'm telling that this is available over here. Okay, once we have this particular ship and the seawater module is available, then I am ready for the antenna placement for this particular thing. I'll be choosing 3 different monopoles at different locations I would like to place them. And in this particular process, I already calculated, I chose these, like the frequencies to be in the megahertz frequencies, like 3 megahertz, 6 megahertz, and 9 megahertz frequencies. Let me go to the construct tab, and I would like to use the line symbol over here, and I would like to use the height for the 3 megahertz. Okay, I already calculated my dimensions for this particular thing. The height of the length of this particular monopole is 23.6 meters. and then I would like to have the position of this particular monopole to be over here. I already had this particular location. I just wanted to tag them appropriately. I'm gonna copy it and I will be pasting it so that it will be much easier. Okay, I got my first monopole is available. Let me keep the second monopole at different location. Let me go back to the second monopole and I'm going to choose my second monopole is working at 6 megahertz and the length of this particular monopole is 11.68 meters and my locations are work plane locations on the ship. I just choose some random locations so that they are appropriate in with respect to their positions. And I'm gonna place that particular thing second monopole. Similarly, I'm gonna keep the third monopole in front of the ship, and I have my length to be for the length at 9 megahertz is approximately 7.8 meters, and the work plane coordinates are 33. X coordinate is 33, and Y coordinate is 0, and my Z coordinate is approximately 7.4. I'm gonna copy it. Okay. Once I define my monopoles over here, you see over here, I got the 3 monopoles that are available at 3 megahertz, 6 megahertz, and 9 megahertz. Let me first union them so that all these things will be available for me. Yes, I'm going to perform the union operation that is available in the construct tab, and I union them. Okay, I do have all the 3 wires. Okay, now I need to make this 3 megahertz monopole to work at. I need to tag this particular thing with a port and a voltage source. Let me go ahead and select the wire 772 and create port. Okay, and I'm going to have the port 1 create. Similarly, let me select the wire for the second monopole antenna, which is working at 6 megahertz. Let me tag with the wire port, and this is going to be port 2. Then let me go to the third antenna and then let me create the wire port 3. Okay, 3 antennas were there. And I can tag the port 1 to the source, right? As I told you, I need to tag this particular thing to a voltage source. Let me create a voltage source over here. You can right click and choose the voltage source, create. Otherwise, you can go to the source or load tab and you can access the wire ports and voltage sources as well. Because since it is really handy, I'm just accessing everything in this particular toolbar over here, model browser. Okay, I can go to the frequency and I would like to assign this particular thing. I know this particular thing will be working at 3 megahertz. Click OK. And what I wanted my far field for this particular monopole antenna, which I placed on the ship. What is that I wanted? I wanted the far field pattern. Let me select the far field over here and 3D. Okay, just I wanted to offset this particular reflection far field pattern because it is, you see, it is basically origin, it is located at the origin. I just wanted to use my offset coordinates where I kept the antenna. I'm going to use them. I have minus 60, of course, then I have 0 and my Z coordinate is 5.5 approximately. That is the coordinate I would like to use for my Z coordinate, and these are the coordinates for my far field pattern. Okay, that whatever you compute the far field pattern for 3 megahertz will be available for you. And just hit create button. Very simple. Now I would like to do the same things for 6 megahertz and 9 megahertz as well. It's in the same setup without going anywhere. And also I would like to request the S parameters so that I can compute the coupling between these antennas, 3 megahertz antenna with respect to 6 megahertz antenna, 3 megahertz with respect to 9 megahertz antenna, similarly 6 megahertz antenna with the other antennas, and also the same thing 9 megahertz antenna with the other antennas as well. Okay, I'm going to set up, look at this. This is very interesting and very critical now. And let me copy this particular configuration and do it for 6 megahertz and 9 megahertz. And before doing that, I would like to make this particular configurations specific so that you can do every simulation in this one chunk rather going outside of this particular CAD Feko session. We are going to select the frequency per configuration, sources per configuration, loads per configuration in case we are using also power configuration. That means everything is unique on its own configuration. Let me rename this thing as 3 megahertz so that this will be as 3 megahertz. Okay, so that it will be easy for our understanding purposes. And let me go to the next thing was the currents. Also, I would like to request the currents for this particular ship. I would like to go to the request tab and I would like to request the currents. Not only the far field pattern, I would like to request how the currents will be distributed at 3 megahertz. Yeah, as I told you, I would like to set up the same thing for 6 megahertz and 9 megahertz. I would like to duplicate this particular configuration, copy, duplicate, and I have this particular thing as 3 megahertz underscore 1. I would like to rename this thing as 6 megahertz. Okay, that means I am computing the analysis for 6 megahertz. Let me change the frequency over here to 6 megahertz. Okay, and I would like to tag the appropriate voltage port to this particular thing. I would like to tag the port to port 2 because this is the one which is going to work for us. Apply. And I want to change the far field pattern as well. Far field pattern for this is 6 megahertz is over here. I would like to shift this particular thing to the appropriate coordinate. What are my coordinates? My coordinates are 6.3 is my x coordinate. And similarly, y coordinate is 0 and z coordinate is 18.13. Okay, I have all my coordinates are available for my 6 megahertz application. Okay, similarly, currents for 6 megahertz are calculated. Then I would like to do the same thing for 9 megahertz. Copy, duplicate, and let me rename this as 9 megahertz. And we have the problem set up for 9 megahertz as well. Once I do have the 9 megahertz, I'm going to choose the frequency as 9 megahertz over here. Then I would like to change the work far field coordinates to be work plane coordinates to be tweaked appropriately based on the antenna location so that they will be visible appropriately. Okay, I got the 33, and for the y coordinate it is 0 and the z coordinate is approximately 7.4. I would like to get that particular thing approximately, and you see over here all these things were placed appropriately. And last but not least, we do have the patterns antenna location, what I can far field patterns. Once we place the antennas, we could calculate. As I mentioned, I would like to calculate the S parameters, which is very important for the collocation interference. I would like to use this particular S matrix values for further analysis using the cosine and interference analysis purposes. Let me request the S parameter matrix as well. You go to the request tab and go to the S parameters. Okay, I'm going to go to the add port. I would be choosing the port 2 and port 3. Okay, I have port 1, port 2, and port 3. I can get all the 9 elements, diagonal elements and off diagonal elements, everything I'll be getting it, and I can get all the coupling elements as well. Create. Okay, I do have all the necessary things that are available. For the S parameters, I would like to choose from 3 megahertz to 9 megahertz. Just for the time being, I'm choosing 3 megahertz to 9 megahertz as a continuous sweep so that it can get the S parameter coupling values for all these frequencies. Okay, then this is how we are going to set up, and then let me save this particular model on the desktop, or I can give it as a demo one. And let me save this particular thing as ship antenna placement, right? Ship and antennas. I'm going to keep the name as ship and antennas. Okay, once I have this particular thing available, I can, as I told you, I can go to the solve or run tab and I can use the Feko solver button and I can look into all the results. Yes, just we'll hit that particular thing. And as I already solved it, will take a little bit of time. I already solved that particular model that is available. I'm going to open that particular thing and you can see over here all the currents and the antenna pattern are available at 3 megahertz. You can see over here the currents what we requested on the ship we have over here. Similarly, the radiation pattern. And also we do have for the 6 megahertz antenna, we also computed the far fields and the currents at 6 megahertz. Similarly, for the 9 megahertz, we could able to compute the radiation pattern and the currents as well. Okay, I just would like to animate certain things so that we can see the effects of the currents on the ship over here. I just deactivated the far field, just hide that particular thing so that we can see the current effects on this particular ship. Let me go to the animate button and choose the phase so that we can observe the phase variations of the current on the ship. Okay, because of this particular monopole antenna. Okay, that is really cool to see this particular thing, which visually. Then I can jump on to our what I can call look into the S matrix, right, which is very important. You can see over here as I requested the S matrix over here from here we can see from 2.5 megahertz to 10 megahertz. That's why that's what I calculated. I could able to get all the S matrix elements over here, S11, S22, S33, and also you can plot the off diagonal elements. Okay, you can see over here all the 9 elements are available for us from this particular simulation. We can use S11, S12, all the things that are available. We are going to use this S matrix elements of diagonal elements, and then we are going to go to the coupling matrix that we are going to take this particular coupling matrix information and we are going to punch into the co-site interference. You can see over here the coupling, right? As I told you, S31, how the first antenna is getting coupled to the port 3, right? Port 1 to port 3. That means 3 megahertz is radiating and 9 megahertz is receiving. How it is working at. That's what we would like to compute this particular thing. And then let me show one more thing over here before jumping into this particular co-location interference. You see here as one of the slides Dr. CJ was talking about in the application macro, there is a script available for plotting the S matrix interference. You can see over here in the macro library S parameter calculators, you can plot the interference matrix as well inside Feko without going there. In case if you would like to do that particular coupling levels and all, you can do that particular thing over here in this particular post Feko script itself. Okay, I'm not doing that, just I'm telling that the script is available for you for calculation purposes. Then let me go back to the what I can call the wrap software that is available over here. Since I already set up everything over there, I just would like to demonstrate the things for you. Okay, the wrap is basically comes with the 2 windows. One is project window and the other thing is the map window. Okay, one thing is we can see the graphically and we can punch in everything over here. Let me tweak the window so that you can see these things perfectly. Okay, you can have this information both the map view and what I can call and the project view. Okay, whatever you do, you can do it over here. All the calculators and everything is available in the project window. And the map window, you can graphically visualize them in case you should place the antenna where it is existing and the stuff like that. And then let me go back to the project window where we are there and describe the problem. We did calculate this parameter matrix, right? From the Feko. We got the radiation patterns, we got the currents, we got the S parameter coupling matrix. We need to have the connection now between the S parameter matrix and the CAD Feko session. Okay, then let me go to the Feko sites, and this is how we are going to set up everything. Okay, Feko, this is what you can see over here. I do have the coupling matrix, which I got that particular thing from Feko. I entered over here all the things. And then I do have the stations, right? Like 3 stations you can see over here. I do have the 3 megahertz antenna. And of course, I will be having this particular thing, the location values. You see here, where do I need to place this particular antenna? Yes, you can also have that particular provision and the frequencies and the transmission information, everything is available. Similarly, for 6 megahertz, you are going to define all the things for the location and the transmission information, transmitter equipment information, the frequency information, everything. Yeah, I'll just follow the same procedure for 9 megahertz. I do have the 3 antennas that are placed on this particular ship. If you don't take that as parameter values, you can just use, because basically once you use this particular tool, inbuilt based on the locations and all the things, it can calculate one coupling matrix. But we are not interested in that particular thing. We are interested only on these values, that what we got from Feko. We will be taking these parameters and we'll be punching them into this particular coupling matrix over here. Okay, I already had those parameters, as I told you. I entered those information in the coupling matrix information over here. Once I enter this particular thing, very straightforward, I can go to the what I can go to the tools information over here, tools tab in the project window. I can just hit the collocation interference. It can calculate for the adjacent interference. It can calculate the harmonic interference, and also apart from that, there are a lot of other components. Also, it can measure that particular thing. As a topic of interest, we will be talking about the adjacent interference and the harmonic interference. Let me perform the collocation interference. Okay, and let me how they are getting interfered. Let me select all these things and go to the calculate and calculate interference. It is going to do the job for us, and it is going to provide us how the interference elements, how it is going to interfere. You see here, I opened the 6 megahertz antenna. It has a cosine adjacent interference from 3 megahertz antenna and 9 megahertz antenna. And I can look at the values, how they are. Yeah, from 3 megahertz antenna, I got like a minus 8.0 dB. That is the parameter which we will decide how effectively it is affecting the antenna. Okay, and also 9 megahertz, I got a 9.8. And see, let me check for the harmonic interference. Yeah, harmonic interference, we got a big number like minus 59, which is not acceptable. We need to take an action over here by adding some filter or something like that from this part at this particular 3 megahertz. Let us see for the 9 megahertz antenna how it is behaving. Yeah, similarly for 9 megahertz antenna, I do have the co or adjacent channel interference values from 3 megahertz is like this, and 6 megahertz I got minus 10.5, and also I do have the harmonic interference as minus 4.5. The harmonic interference values are really high. That means we need to take a step. You can add an equipment like a filter or something like that. Otherwise, you can come up with some of your own plan of action there. For here, I would like to add a filter at 3 megahertz antenna so that it can minimize or eliminate my harmonic interference at 6 megahertz antennas or 9 megahertz antenna. Let me go back to 9 megahertz antenna and add a filter at that particular frequency. Okay, let me choose frequency, and I'm going to add the antenna that is available in the library. I'm going to use a 70 megahertz antenna. Don't worry, it is even though it is at 70 megahertz, it is going to automatically tune to the frequency appropriately what we are using on our transmitter antenna. Okay, and I have this particular antenna filter brought into the antenna profile. Okay, I have a filter, then I have the antenna, so that this can help us to eliminate the harmonic interference. That's what as you told that I added a filter over here. Let me go to the click OK button, and again we'll do the same analysis what we have done. Let me select the 3 antennas and go to the tools and perform the collocation interference. Okay, and select these 3 things again, go over there and perform the calculate interference. Okay, I do have the 6 megahertz antenna, and let me look for the harmonic interference, because you see here it was earlier almost minus 59.5. It got reduced to minus 8.5. Similarly, for 9 megahertz, it got reduced to minus 8. Okay, that's how we can eliminate the harmonic interference, or we can minimize the harmonic interference by adding the equipment to the antennas. That part can be easily done using RAP, the collocation interference module that is available inside RAP. RAP itself, it's a very big software. It has several modules, but as a topic of interest is collocation interference, I would like to present this particular thing. One more thing I would like to add before ending this particular demo part. As you can see over here, we do have antennas for the platform and all, whatever we could be able to get it. Similarly, one can set up the same problem for the aircraft as well. Okay, think like that. In one of the CJ's slides, couple of slides, he was talking about the antenna collocation interference for the aircrafts. We can mimic the same workflow or same strategy, whatever we are doing to the aircraft modules as well. Okay, with this, I hope you enjoyed the little demonstration over here. I hope you